Thank you all for being here. I have a difficult task after Yoni's presentation because I'm going to try to argue that that money matters and, and that markets that markets are important. Although I do realize that for markets to work, you certainly need to have the predisposition. The issue is, you see, is the ethos coming first, or is the success in money coming first? Thinking of the Protestant ethic. So what came first? The success of those Protestants in doing well, or economically, or the Protestant ethic? Anyway, so just to provide some framework. The outline, here's what I'm going to talk about. Say a few things about the electric grid idiosyncrasies, the fact that generation and demand are very similar in being able to provide functionality and scope and dynamics that are important for the secure and efficient operation of the power system. And then I'm going to say a few things about markets. What are markets today? What's the functionality, the scope, the timescales, and argue that reforms are needed to embrace the participation of demand, which is what I'm going to be arguing for, participation of demand on a par basis with generation. And then I'll say a few things about research directions that I think are interesting and which are pursued by people in this room, people at BU and people in this room from industry and from the academic institutions, MIT and Tufts and so on. So it's a good idea to think of the smart grid as something that's holistic, that covers everything from centralized generation, transmission, distribution, going all the way to our meters and our appliances. Distributed generation is part of it. See that the direction of flow of energy is about to go in both ways. See that the that automation and measurement and so on is going to play a very big role in the evolution of the smart grid, and that all of this provides a fertile ground for control and for system science to make a difference. There are lots of cyber components already in the smart grid, which is not as dumb as one might think from its current name, but there are emerging capabilities. Arguing that demand and generation are kind of mirroring each other in terms of their capabilities, one can look at a series of characteristics. The dispatchability, schedulability of loads and of demand. There are certain types of generation that are more dispatchable than others. Renewable generation, for example, is not dispatchable at all, whereas combustion turbines are very dispatchable, schedulable, and you have the whole range. Mothballed plants need 2 or 3 days to come online. They are less dispatchable. Same thing with generation. You can schedule some generation. You can't schedule other types of generation. Flexibility is also very important. Can we modulate in the short run? Can we have sort of dynamical, can we elicit dynamical behavior from generation, from demand? Again, there are types of generation that you can do that more easily than others. And there are many loads that have high flexibility and others that have low flexibility. For example, lighting, we are not as flexible with lighting. We're more flexible with appliances, duty cycle type of appliances, etc. And we are much more flexible with certain types of industrial consumption of energy, such as the liquefaction of gases and so on. Forecastability. Are we able to forecast the output from generation? Yes, on some, no on others. There's not as well on others. So wind generation, for example, can be forecasted a day ahead with a 20% error. Some of the types of demand, conventional inflexible demand, can be forecasted again, but depending on the scope, on the geographical region that you're trying to forecast, the error is 2, 3, 4%. And other types of demand, of course, we can forecast, we can schedule. And likewise, we can forecast the output of some generation sources. And finally, voltage control, which is very important, is something that we have been almost exclusively doing on the generation side, but now we can do a lot on the demand side, particularly with asynchronous motors, particularly with all sorts of microelectronics that accompany new loads, accompany new resources that are becoming available, and these new resources can be used can be put into dual use. So, what are the idiosyncrasies of the power system? Alternating current requires a synchronization of a huge machinery spread around that has to operate in synchrony at the same frequency. We have very small synchronization tolerance. We have to maintain the energy balance almost in real time. And in order to do that, because of the uncertainties in forecastability, in controllability, and so on, we need, in addition to energy, to make sure that we set aside certain reserves. And the reserves are not jelly. They're not the same thing. There are different types of reserves with different types of dynamics. We call them roughly primary, secondary, and tertiary. But there are more than 3 types of reserves. And these have different time scales. So the primary reserves are managed. We secure them in advance, but they are managed in almost real time. The secondary reserves, we secure them ahead of time, but they are managed with a 5-minute time scale, and the tertiary reserves, 5-second, time scale, whereas the tertiary reserves are managed in what we call almost real-time markets, the 5-minute markets, every 5 minutes. And finally, we have congestion over the transmission system, which links everybody together. And this congestion has to be captured by modeling the flow of power following the laws of physics rather than some more convenient fashion that we want to model them with. Unfortunately, that's that. So when we look at the decoupling or decomposition of the smart grid, we have centralized generation and decentralized consumption, generation, and resources that are competing, that may develop as competing agents in the market, whereas the network is a natural monopoly that has to be controlled and to avoid congestion and so on. And the way you control it, fortunately or unfortunately, has impacts on the way that markets operate. So that's very important to see the relationship, the interrelationship of optimally managing the transmission system and the distributional impact that this may have through the proper operation of markets. Very quickly, what sorts of markets do we have now? First of all, markets clear energy and reserves, these three types of reserves. And markets are cascaded. So we have the day-ahead market that clears and schedules demand, schedules energy and reserves for every hour. We have the adjustment markets that do the same after a disturbance takes place. We have the hour-ahead market. We have the 5-minute market that operates on a 5-minute basis. And all of these markets clear things in some sort of a central fashion. The ISO, Eugene's colleagues clear these markets at ISO New England and in the other independent system operators around the country where you have power markets. But whereas all of these markets clear energy and reserves, it's only the 5-minute market that actually manages the slowest of these three reserves that I mentioned, namely the tertiary reserves. If you want to look at the actual management of reserves, which are there to maintain the energy balance so that we have stability and so on, then this takes place under some central coordination, as, for example, primary reserves or frequency control, which takes place in real time according to a set rule and according to a signal, the frequency that's available, which you can think of as being recovered, as being sort of a centrally broadcasted. I mean, it's a system characteristic. And the secondary reserves are managed through a signal that is sent every 4 to 8 seconds, depending on the system operator, let's say every 5 seconds, which then has to be heeded by decentralized response to it from those who have provided those secondary reserves regulation service. So here is an example of this every 5 seconds, or every 4 seconds in this case, regulation signal. There are two types of regulation signals. This is from PJM. And that signal varies from -1 to +1. And then this centralized signal recovers a response from each provider, which adds up to some portion of the total secondary reserves that were secured, capital S, from the system operator. So these SIs, these promises, are secured in the markets, by the market in advance, efficiently and through market-based price discovery, but their actual management, right, takes place, their actual use takes place through a centralized signal. And therefore, I call this centralized signal that coordinates distributed response by all those providers. So the I index identifies providers of secondary reserves who have to respond accordingly to track this signal. They've been paid when they promised this amount of reserves, but then if they don't do a good job to actually respond appropriately, then they lose some of their pay. At least PJM is introducing a penalty, clearly a penalty, according to how well the various providers respond. So I have here the PJM definition of how this signal, which you can see every 4 seconds, right? These are the super fast and the fast secondary reserves. By fast, I mean that the bigger ramp rate is presumed on one type than on the other. So that signal is being sent as the result of a proportional integral filter from the area control error, which is what is happening in the larger balancing area that the independent system operator manages. And then that signal has to then be heeded by individual participants. So here is some real data of a combined cycle unit that's doing frequency control here. This is following frequency deviations. And here it's doing secondary regulation service by following this Y signal. Question is, given renewable generation, which is going to increase the difficulty that we have with forecasting, if not demand net of generation from renewable, non-dispatchable, non-controllable, intermittent generation sources, which we hope will increase in importance as we go forward. Then we will need more reserves. And in order to be able to meet these reserves, to satisfy this, to be able to provide these reserves at a reasonable cost so that we are not only sustainable environmentally, but we are also sustainable in terms of what we are doing economically, in terms of security of supply and so on, we have to bring in the demand side. Do we need to, and the question is, do we need to redesign markets in order to do that, or are existing markets fine where they are? Well, one area where I think we need to redesign is the multi-period markets, such as the day-ahead market, where right now, in order to participate, you are only allowed to express your utility, your desire to consume, as if the utility that you are deriving from consumption is additive over time. Well, that's true with certain inflexible loads, but not true as regards flexible loads. So that's a fallacy, and therefore we need different ways of expressing the utility, so that utility is coupled with time, so that utility represents the achievement of a certain state variable that may be related to cumulative past consumption, but is not myopically related to the current consumption. So, for example, when you look at electric vehicles, an electric vehicle doesn't care about how much it consumes this hour and next hour to charge its battery, as long as the state of charge of the battery is whatever it wants it to be at the time it wants to depart, and it can hedge. It may want 80% of the battery to be full by a certain time, lest that person would decide to leave, and 100% later, and so on and so forth. And it's only with respect to that state, the state of charge, that there is a utility that's identified. And that utility, of course, you can easily quantify in terms of the opportunity cost of using gasoline if you have a plugged-in hybrid electric vehicle to make up the amount of energy that you didn't, the amount of electricity that you didn't charge. So expressing this utility and providing this utility together with how the state variable that is associated with a utility varies with consumption is another way of being able to bid. And if you bid this way, then the market can clear and schedule you at the lowest cost hours and charge you your actual cost, which will be the minimum cost. Same thing you can say about other types of loads, such as duty cycle type of loads that are involved with heating, where you have certain degrees of freedom, and where the utility is derived from a state variable, the temperature in this case, rather than consumption. So there are certain degrees of freedom. As long as you are within the comfort zone, your utility is fine. And when you get out of those, the problem arises. So with multi-period market, how can multi-period markets clear with these new bidding rules that have to be available together with the old ones, because we have inflexible loads and flexible loads? The market clearing algorithms are still tractable as long as you maintain some amount of linearity. For example, the Italians have created a market clearing tool, Khan remembers that, where you had to have up to a few million of bidders representing loads, perhaps load representatives, load aggregators, and still the algorithm cleared as long as you have, you don't introduce significant nonlinearity. Is competitive equilibrium achievable? Well, you know, we've done some work, and if you have many participants who try to guess the clearing price, self-schedule, in other words, following the current rules, and then you iterate, and these guys update the forecast of prices in a reasonable fashion, then things converge to the same Nash equilibrium that you converge if you have the complex bid. You can do similar things if you're interested in reining in volatile wind generation bids. So if in the future, when we get a lot of wind on board, we stop subsidies and so on, and we have wind generators bid just like everybody else, those wind generators should be also responsible when they bid aggressively, meaning if in the day-ahead market they bid at some high estimate of their possible output, they should be responsible for the additional reserves that they make necessary, and those additional reserves could possibly be estimated on the basis of forecasting, which is done by a third party, a practice that's actually taking place in Spain, in Denmark, and so on, where you already, right now, where you have extensive integration of wind generation. So volatile wind generation under these simple complex bids or extended types of bidding can be induced to bid appropriately without being overly aggressive, in the sense that they are responsible for the cost of the reserves that they make possible. So one could combine all of these things, have the load side bid for energy and for reserves, the flexible loads, have wind generation and volatile renewable generation bid, revealing also the reserve requirements and knowing that they will be charged for the reserve requirements that they make necessary, but without knowing in advance what the clearing price of the reserves is going to be. So that's the idea of bidding without needing to forecast the outcome of the markets. In hour-ahead bidding, it's an issue on how to bid. So flexible loads can bid for energy and for reserves, and the market clears and gives them either energy only or reserves and energy or nothing, depending on the prices that they bid for energy and for reserves, the capacity that they have that provides a trade-off of how much energy and how many reserves, how much energy you can consume and how many reserves in both directions, because regulation service, at least in New England, PJM and so on, are two-directional. You can provide, and the market then decides how to split your bid into energy consumption, into reserve provisioning, energy only or nothing at all, depending on your bids and the market clearing prices. So this is essentially the outcome of, these are the clearing prices for reserves and for energy, for secondary reserves in this case. And the segmentation of the market outcome events is based on the bids. Moreover, can we ignore the distribution network and the costs associated with the distribution network? If you remember the earlier slide that I showed you, a big portion of the overall cost, about a third, is associated with the distribution network. So wholesale power markets today reflect absolutely nothing in terms of the costs at the distribution network. Losses, local constraints, voltage control, and so on. So therefore, it is important to be able to incorporate the costs and reflect these costs of the distribution network to the overall price. So then the energy clearing price P for real power at some location B, at some bus B, in a feeder, in a low level, in a low voltage feeder, should depend on the clearing price at the swing bus. And by the swing bus, I denote here the cost of energy at the substation increased by the marginal losses, the equivalent for reactive power, an additional of how the voltage magnitudes are affected by real power, times the Lagrange multiplier of the voltage tolerance constraint. Of course, this would be 0 if you don't need voltage control. And then you can have additional terms for the wear and tear of transformers. And it turns out, so here is a baby system that we've been playing with. This is one branch of the distribution network. So you have medium voltage here and 3 feeders with a few residences or commercial or industrial consumption levels. And so here you have the low voltage, and depending on what you consume or generate at every level, you affect voltages, flows, losses, and so on and so forth. And the interesting thing is that you are able to control, in some cases, reactive power as well because of the power electronics that are available. So here's an example to go to the very small of what you can do in a building where you have central heating and cooling with a variable speed fan that sends air around, and perhaps you have some photovoltaics on the roof. Here is what you can do from a systems point of view to optimize the consumption of energy and the use of energy that you generate, and also provide reactive power to the to decrease losses in the distribution network, and to also provide voltage control. So first of all, your your rooftop photovoltaics can take advantage of the power electronics that convert AC to DC, that is then further converted to alternating current that drives the variable speed drive. So you have about maybe 400 volts here of DC. You have maybe 20 volts of DC produced from your photovoltaics. Rather than losing about 10% of that energy to convert it back to AC and send to the grid, you can lose only 2 or 3% to increase its voltage with a smaller, limited amount of microelectronics, and therefore you render the cost of your photovoltaics installation smaller, and you convert it here to direct current, and you use it right away without having to convert AC, and then you can send it back, and the additional capacity the additional capacity of reactive power you can utilize to help with voltage control, decrease losses, and so on and so forth. So these are some ideas, research directions, new multi-period market rules. Are they tractable? Are they stable? Do they have a stable equilibrium? Are they robust to gaming and market manipulation? These are important questions that many people here in the audience, Mark Davidge and others, are working, and Anu, of course, and Munther. Optimal market bidding of energy and reserves by location-specific load aggregators, load representatives. Price offered by these people to individual consumers. For example, I plug in my vehicle, I say I want to depart at this time. What would be the cost of charging me by the time that I want to depart? How can this be calculated? Distribution network pricing that I talked about before, involving losses and everything. The management of regulation service, which is a very important area where we've been doing work that is based on sort of having a virtual market in a smart building or in a neighborhood where price signals can allow you to control and manage duty cycle equipment and charging of batteries and so on. And then finally, the non-competitive segment of the grid. How can we control it? By doing two things: dynamically switching on and off some lines that are not overloaded, but which can redirect the power flows and decrease congestion. And how can we coordinate this with the management of phasor angle regulators that are being more and more represented in the grid. So anyway, this is a multidisciplinary approach. So I'm going to raise a white flag to Yoni and say, let's join hands. This is a very rich and fertile research opportunity set that's ahead of us.